Purpose and scope. Ground reference maneuvers and their related factors are used in developing a high degree of pilot skill. Although most of these maneuvers are not performed as such in normal everyday flying, the elements and principles involved in each are applicable to perform mance of the customary pilot operations. They aid the pilot in analyzing the effect of wind and other forces acting on the powered parachute, and in developing a fine control touch and the division of attention neces sary for accurate and safe powered parachute maneuvering. All of the early part of the pilot's training has been conducted for the purpose of developing technique, knowledge of maneuvers, feel, and the handling of the powered parachute in general. This training will have required that most of the pilot's attention be given to the actual handling of the powered parachute, and the results of control pressures on the action of the powered parachute. If permitted to continue beyond the appropriate training stage, however, the student pilot's concentration of attention will become a fixed habit, one that will seriously detract from the student's ease and safety as a pilot, and will be very difficult to eliminate. Therefore, it is necessary, as soon as the pilot shows proficiency in the fundamental maneuvers, that the pilot be introduced to maneuvers requiring outside attention on a practical application of these maneuvers and the knowledge gained. During ground reference maneuvers, it is important that basic flying technique previously learned be maintained. The flight instructor should not allow any relaxation of the student's previous standard of technique simply because a new factor is added. This requirement should be maintained throughout the student's progress from maneuver to maneuver. Each new maneuver should embody some advance and include the principles of the preceding one in order that continuity is maintained. Each new factor introduced should be merely a step up of one already learned so that orderly, consistent progress can be made. Maneuvering by reference to ground objects. Ground track or ground reference maneuvers are performed at a relatively low altitude while applying wind drift correction as needed to follow a predetermined track or path over the ground. They are designed to develop the ability to control the powered parachute and to recognize and correct for the effect of wind while dividing attention among other matters. This requires planning ahead of the powered parachute, maintaining orientation in relation to ground objects, flying appropriate headings to follow a desired ground track, and being cognizant of other air traffic in the immediate vicinity. Pilots should perform clearing turns prior to beginning a maneuver. The essential idea of the clearing turn is to be certain that the next maneuver is not going to proceed into another aircraft's flight path. Some pilot training programs have hard and fast rules, such as requiring two 90-degree turns in opposite directions before executing any training maneuver. Other types of clearing procedures may be developed by individual flight instructors. Whatever the preferred method, a clearing procedure should be used. Execute the appropriate clearing procedure before all turns and before executing any training maneuver. Proper clearing procedures, combined with proper visual scanning techniques, are the most effective strategy for collision avoidance. Ground reference maneuvers should be flown so as not to descend below 200 feet above the ground. The actual altitude will depend on a number of factors. You should plan and fly the maneuver so as not to descend below an altitude of 200 feet above ground level, AGL. However, you must also plan and fly so as not to come closer than 500 feet to any person, vessel, vehicle or structure. The radius of the turn and the path of the powered parachute over the ground should be easily noted and changes planned and effected as circumstances require. Drift should be easily discernible, but not tax the student too much in making corrections. The altitude should be low enough to render any gain or loss apparent to the student, but in no case closer than 500 feet to the highest obstruction or lower than 200 feet above the ground. During these maneuvers, both the instructor and the student should be alert for available forced landing fields. The area chosen should be away from communities, livestock, or groups of people to prevent possible annoyance or hazards to others. Due to the altitudes at which these maneuvers are performed, there is little time available to search for a suitable field for landing in the event the need arises. Drift and ground track control. Whenever any object is free from the ground, it is affected by the medium with which it is surrounded. This means that a free object will continue to move in its current direction and speed unless acted upon by another force. For example, if a powerboat is crossing a river and the river is still, the boat could head directly to a point on the opposite shore and travel on a straight course to that point without drifting. However, if the river were flowing swiftly, the water current would have to be considered. That is, as the boat progresses forward with its own power, it must also move upstream at the same rate the river is moving it downstream. This is accomplished by angling the boat upstream sufficiently to counteract the downstream flow. If this is done, the boat will follow the desired track across the river from the departure point directly to the intended destination point. Should the boat not be headed sufficiently upstream, it would drift with the current and run aground at some point downstream on the opposite bank. Figure 9.1. As soon as a powered parachute becomes airborne, it is free of ground friction. Its path is then affected by the air mass in which it is flying, therefore, the powered parachute, like the boat, will not always track along the ground in the exact direction that it is headed. When flying with the longitudinal axis of the powered parachute aligned with the road, the powered parachute may get closer to or farther from the road without any turn having been made. This would indicate the air mass is moving sideward in relation to the powered parachute. Since the powered parachute is flying within this moving body of air wind, it moves or drifts with the air in the same direction and speed, just like the boat moved with the river current. See Figure 9.1. When flying straight and level and following a selected ground track, the preferred method of correcting for wind drift is to head the powered parachute sufficiently into the wind to cause the powered parachute to move forward into the wind at the same rate the wind is moving it sideways. Depending on the wind velocity, this may require a large wind correction angle or one of only a few degrees. When the drift has been neutralized, the powered parachute will follow the desired ground track. To understand the need for drift correction during flight, consider a flight with a wind velocity of 30 knots from the left and 90 degrees to the direction the powered parachute is headed. After 1 hour, the body of air in which the powered parachute is flying will have moved 30 nautical miles to the right. Since the powered parachute is moving with this body of air, it too will have drifted 30 nautical miles to the right. In relation to the air, the powered parachute moved forward, but in relation to the ground, it moved forward as well as 30 nautical miles to the right. There are times when the pilot needs to correct for drift while in a turn. Figure 9.2. Throughout the turn the wind will be acting on the powered parachute from constantly changing angles. The relative wind angle and speed govern the time it takes for the powered parachute to progress through any part of a turn. This is due to the constantly changing ground speed. When the powered parachute is headed into the wind, the ground speed is decreased. When headed downwind, the ground speed is increased. Through the crosswind portion of a turn, the powered parachute must be turned sufficiently into the wind to counteract drift. To follow a desired circular ground track, the wind correction angle must be varied in a timely manner because of the varying ground speed as the turn progresses. The faster the ground speed, the faster the wind correction angle must be established. The slower the ground speed, the slower the wind correction angle must be established. You will see then that the PPC should have the steepest bank and fastest rate of turn on the downwind portion of the turn and have the shallowest bank and slowest rate of turn on the upwind portion. The principles and techniques of varying the angle of bank to change the rate of turn and wind correct tie and angle for controlling wind drift during a turn are the same for all ground track maneuvers involving changes in direction of flight. When there is no wind, it should be simple to fly along a ground track with an arc of exactly 180 degrees and a constant radius because the flight path and ground track would be identical. This can be demonstrated by approaching a road at a 90 degrees angle and, when directly over the road, rolling into a medium bank turn, then maintaining the same angle of bank throughout the 180 degrees of turn. Figure 9.2. To complete the turn, the rollout should be started at a point where the canopy will become level as the powered parachute again reaches the road at a 90 degrees angle and will be directly over the road just as the turn is completed. This would be possible only if there were absolutely no wind, and if the angle of bank and the rate of turn remained constant throughout the entire maneuver. If the turn were made with a constant angle of bank and a wind blowing directly across the road, it would result in a constant radius turn through the air. However, the wind effects would cause the ground track to be distorted from a constant radius turn or semicircular path. The greater the wind velocity, the greater would be the difference between the desired ground track and the flight path. To counteract this drift, the flight path can be controlled by the pilot in such a manner as to neutralize the effect of the wind, and cause the ground track to be a constant radius semicircle. The effects of wind during turns can be demonstrated after selecting a road, railroad, or other ground reference that forms a straight line parallel to the wind. Fly into the wind directly over and along the line and then make a turn with a constant medium angle of bank for 360 degrees of turn. Figure 9.3. The powered parachute will return to a point directly over the line but slightly downwind from the starting point, the amount depending on the wind velocity and the time required to complete the turn. The path over the ground will be an elongated circle, although in reference to the air, it is a perfect circle. Straight flight during the upwind segment after completion of the turn is necessary to bring the powered parachute back to the starting position. A similar 360 degrees turn may be started at a specific point over the reference line, with the powered parachute headed directly downwind. In this demonstration, the effect of wind during the constant bank turn will drift the powered parachute to a point where the line is re-intercepted, but the 360 degrees turn will be completed at a point downwind from the starting point. Another reference line which lies directly crosswind may be selected and the same procedure repeated, showing that if wind drift is not corrected the powered parachute will, at the completion of the 360 degrees turn, be headed in the original direction but will have drifted away from the line a distance dependent on the amount of wind. From these demonstrations, you will see where and why it is necessary to increase or decrease the angle of bank and the rate of turn to achieve a desired track over the ground. The principles and techniques involved can be practiced and evaluated by the performance of the ground track maneuvers discussed in this chapter. Rectangular course. Normally, the rectangular course is the first ground reference maneuver the pilot is introduced to. Figure 9.4. The rectangular course is a training maneuver in which the ground track of the powered parachute is equidistant from all sides of a selected rectangular area on the ground. The maneuver simulates the conditions encountered in an airport traffic pattern. While performing the maneuver, the altitude should be held constant. The maneuver assists the student pilot in perfecting practical application of the turn. The division of attention between the flight path, ground objects, and the handling of the powered parachute. The timing of the start of a turn so that the turn will be fully established at a definite point over the ground. The timing of the recovery from a turn so that a definite ground track will be maintained. The establishing of a ground track and the determination of the appropriate crab angle. Like those of other ground track maneuvers, one of the objectives is to develop division of attention between the flight path and ground references, while controlling the powered parachute and watching for other aircraft in the vicinity. Another objective is to develop recognition of drift toward or away from a line parallel to the intended ground track. This will be helpful in recognizing drift toward or from an airport runway, landing area, during the various legs of the airport traffic pattern. For this maneuver, a square or a rectangular field, or an area bounded on four sides by section lines or roads, should be selected well away from other air traffic. The powered parachute should be flown parallel to and at a uniform distance from the field boundaries, not necessarily directly above the boundaries. For best results, the flight path should be positioned outside the field boundaries just far enough that they may be easily observed from either pilot seat by looking out the side of the powered parachute. If an attempt is made to fly directly above the edges of the field, the pilot will have no usable reference points to start and complete the turns. The closer the track of the powered parachute is to the field boundaries, the steeper the bank necessary at the turning points. Also, the pilot should be able to see the edges of the selected field while seated in a normal position and looking out the side of the powered parachute during either a left-hand or right-hand course. The distance of the ground track from the edges of the field should be the same regardless of whether the course is flown to the left or right. All turns should be started when the powered parachute is abeam the corner of the field boundaries headed downwind where ground reference maneuvers are typically started. These should be the determining factors in establishing the distance from the boundary for performing the maneuver. Although the rectangular course may be entered from any direction, this discussion assumes entry on a downwind. On the downwind leg, the wind is a tailwind and results in an increased ground speed. Consequently, the turn onto the next leg is entered with a fairly fast rate of turn and a higher, medium bank. As the turn progresses, the bank angle is reduced gradually because the tailwind component is diminishing, resulting in a decreasing ground speed. During and after the turn onto this leg, the equivalent of the base leg in a traffic pattern, the wind will tend to drift the powered parachute away from the field boundary. To compensate for the drift, the amount of turn will be more than 90 degrees. The rollout from this turn must be such that as the wing becomes level, the powered parachute is turned slightly toward the field and into the wind to correct for drift. The powered parachute should again be the same distance from the field boundary and at the same altitude as on other legs. The base leg should be continued until the upwind leg boundary is being approached. Once more, the pilot should anticipate drift and turning radius. Since drift correction was held on the base leg, it is necessary to turn less than 90 degrees to align the powered parachute parallel to the upwind leg boundary. This turn should be started with a medium bank angle with a gradual reduction to a shallow bank. As the turn progresses, the rollout should be timed to assure paralleling the boundary of the field as the canopy becomes level. While the powered parachute is on the upwind leg, the next field boundary should be observed as it is being approached, to plan the turn onto the crosswind leg. Since the wind is a headwind on this leg, it is reducing the powered parachute's ground speed, and during the turn onto the crosswind leg will try to drift the powered parachute toward the field. For this reason, the roll into the turn must be slow, and the bank relatively shallow to counteract this effect. As the turn progresses, the headwind component decreases, allowing the ground speed to increase. Consequently, the bank angle and rate of turn are increased gradually to assure that upon completion of the turn the crosswind ground track will continue the same distance from the edge of the field. Completion of the turn with the wing level should be accomplished at a point aligned with the upwind corner of the field. Simultaneously, as the wing is rolled level, the proper drift correction is established with the powered parachute turned into the wind. This requires that the turn be less than a 90 degrees change in heading. If the turn has been made properly, the powered parachute should be the same distance from the field boundary and at the same altitude as on other legs. While on the crosswind leg, the wind correction angle should be adjusted as necessary to maintain a uniform distance from the field boundary. As the next field boundary is being approached, the pilot should plan the turn onto the downwind leg. Since a wind correction angle is being held into the wind and away from the field while on the crosswind leg, this next turn will require a turn of more than 90 degrees. Since the crosswind will become a tailwind, causing the ground speed to increase during this turn, the bank initially should be medium and progressively increased as the turn proceeds. To complete the turn, the rollout must be timed so that the wing becomes level at a point aligned with the crosswind corner of the field just as the longitudinal axis of the powered parachute again becomes parallel to the field boundary. The distance from the field boundary should be the same as from the other sides of the field. Usually, drift should not be encountered on the upwind or the downwind leg, but it may be difficult to find a situation where the wind is blowing exactly parallel to the field boundaries. This would make it necessary to use a slight wind correction angle on all the legs. It is important to anticipate the turns to correct for ground speed, drift, and turning radius. When the wind is behind the powered parachute, the turn must be faster and steeper. When it is ahead of the powered parachute, the turn must be slower and yaw lower. These same techniques apply while flying in airport traffic patterns. Common errors in the performance of rectangular courses are: failure to adequately clear the area, failure to establish proper altitude prior to entry, typically entering the maneuver while descending, failure to establish appropriate wind correction angle resulting in drift, gaining or losing altitude, abrupt control usage, inability to adequately divide attention between powered parachute control, maintaining ground track, and maintaining altitude, improper timing in beginning and recovering from turns, inadequate visual lookout for other aircraft. S-turns across a road. An S-turn across a road is a practice maneuver in which the powered parachute's ground track describes semicircles of equal radii on each side of a selected straight line on the ground. Figure 9.5, the straight line may be a road, fence, railroad, or section line that lies perpendicular to the wind, and should be of sufficient length for making a series of turns. A constant altitude should be maintained throughout the maneuver. Do not go lower than 200 feet. S-turns across a road present one of the most elementary problems in the practical application of the turn and in the correction for wind drift in turns. The application of this maneuver is considerably less advanced in some respects than the rectangular course. However, it is taught after the student has been introduced to the rectangular course in order that he or she may have a knowledge of the correction for wind drift in straight flight along a reference line, before attempting to correct for drift by applying a turn. The objectives of S-turns across a road are to develop the ability to compensate for drift during turns, orient the flight path with ground references, follow an assigned ground track, arrive at specified points on assigned headings, and divide the pilot's attention. The maneuver consists of crossing the road at a 90 degrees angle and immediately beginning a series of 180 degrees turns of uniform radius in opposite directions, recrossing the road at a 90 degrees angle just as each 180 degrees turn is completed. To accomplish a constant radius ground track requires a changing rate of turn and angle of bank to establish the wind correction angle. Both will increase or decrease as ground speed increases or decreases. The bank must be steepest when beginning the turn on the downwind side of the road and must be shallowed gradually as the turn progresses from a downwind heading to an upwind heading. On the upwind side, the turn should be started with a relatively shallow bank and then gradually steepened as the powered parachute turns from an upwind heading to a downwind heading. In this maneuver, the powered parachute should be rolled from one bank directly into the opposite just as the reference line on the ground is crossed. Before starting the maneuver, a straight ground reference line or road that lies 90 degrees to the direction of the wind should be selected, then the area should be checked to ensure that no obstructions or other aircraft are in the immediate vicinity. The road should be approached from the upwind side, at the selected altitude on a downwind heading. When directly over the road, start the first turn immediately. With the powered parachute headed downwind, the ground speed is greatest and the rate of departure from the road will be rapid, so the roll into the bank must be fairly rapid to attain the proper wind correction angle. This prevents the powered parachute from flying too far from the road and from establishing a ground track of excessive radius. During the latter portion of the first 90 degrees of turn, when the powered parachute's heading is changing from a downwind heading to a crosswind heading, the ground speed becomes less and the rate of departure from the road decreases. The wind correction angle will be at the maximum when the powered parachute is headed directly crosswind. After turning 90 degrees, the powered parachute's heading becomes more and more an upwind heading, the ground speed will decrease, and the rate of closure with the road will become slower. If a constant steeper bank were maintained, the powered parachute would turn too quickly for the slower rate of closure, and would be headed perpendicular to the road prematurely. Because of the decreasing ground speed and rate of closure while approaching the upwind heading, it will be necessary to gradually shallow the bank during the remaining 90 degrees of the semicircle so that the wind correction angle is removed completely and the wing becomes level as the 180 degrees turn is completed at the moment the road is reached. At the instant the road is being crossed again, a turn in the opposite direction should be started. Since the powered parachute is still flying into the headwind, the ground speed is relatively slow. Therefore, the turn will have to be started with a shallow bank so as to avoid an excessive rate of turn that would establish the maximum wind correction angle too soon. The degree of bank should be that which is necessary to attain the proper wind correction angle, so the ground track describes an arc the same size as the one established on the downwind side. Since the powered parachute is turning from an upwind to a downwind heading, the ground speed will increase, and after turning 90 degrees, the rate of closure with the road will increase rapidly. Consequently, the angle of bank and rate of turn must be progressively increased so that the powered parachute will have turned 180 degrees at the time it reaches the road. Again, the rollout must be timed so the powered parachute is in straight and level flight directly over and perpendicular to the road. Throughout the maneuver a constant altitude should be maintained, and the bank should be changing constantly to effect a true semicircular ground track. Often there is a tendency to increase the bank too rapidly during the initial part of the turn on the upwind side, which will prevent the completion of the 180 degrees turn before recrossing the road. This is apparent when the turn is not completed in time for the powered parachute to cross the road at a perpendicular angle. To avoid this error, the pilot must visualize the desired half-circle ground track, and increase the bank during the early part of this turn. During the latter part of the turn, when approaching the road, the pilot must judge the closure rate properly and increase the bank accordingly, so as to cross the road perpendicular to it just as the rollout is completed. Common errors in the performance of S-turns across a road are: failure to adequately clear the area, gaining or losing altitude, inability to visualize the half-circle ground track, poor timing in beginning and recovering from turns, faulty correction for drift, inadequate visual lookout for other aircraft. Turns around a point is a training maneuver. Turns around a point is a logical extension of the principles involved in the performance of S-turns across a road. Its purposes as a training maneuver are: to further perfect turning technique, to perfect the ability to subconsciously control the powered parachute while dividing attention between the flight path and ground references, to teach the student that the radius of a turn is a distance which is affected by the degree of bank used when turning with relation to a definite object, to develop a keen perception of altitude, to perfect the ability to correct for wind drift while in turns. In turns around a point, the powered parachute is flown in a complete circle of uniform radii or distance from a prominent ground reference point while maintaining a constant altitude. Do not go lower than 200 feet. The factors and principles of drift correction that are involved in S-turns are also applicable in this maneuver. As in other ground track maneuvers, a constant radius around a point will, if any wind exists, require a constantly changing angle of bank and wind correct tie-in angles. The closer the powered parachute is to a direct downwind heading where the ground speed is greatest, the steeper the bank and the faster the rate of turn required to establish the proper wind correct tie-in angle. The more nearly it is to a direct upwind heading where the ground speed is least, the shallower the bank and the slower the rate of turn required to establish the proper wind correction angle. It follows, then, that throughout the maneuver the bank and rate of turn must be gradually varied in proportion to the ground speed. The point selected for turns around a point should be prominent, easily distinguished by the pilot, and yet small enough to present precise reference. Figure 9.6, isolated trees, crossroads, or other similar small landmarks are usually suitable. To enter turns around a point, the powered parachute should be flown on a downwind heading to one side of the selected point at a distance equal to the desired radius of turn. When any significant wind exists, it will be necessary to roll into the initial bank at a rapid rate so that the steepest bank is attained abeam of the point when the powered parachute is headed directly downwind. By entering the maneuver while heading directly downwind, the steepest bank can be attained immediately. Thereafter, the bank is shallowed gradually until the point is reached where the powered parachute is headed directly upwind. At this point, the bank should be gradually steepened until the steepest bank is again attained when heading downwind at the initial point of entry. Just as S-turns require that the powered parachute be turned into the wind in addition to varying the bank, so do turns around a point. During the downwind half of the circle, the powered parachute's nose is progressively turned toward the inside of the circle. During the upwind half, the nose is progressively turned toward the outside. The downwind half of the turn around the point may be compared to the downwind side of the S-turn across a road. The upwind half of the turn around a point may be compared to the upwind side of the S-turn across a road. As the pilot becomes experienced in performing turns around a point and has a good understanding of the effects of wind drift and varying of the bank angle and wind correction angle as required, entry into the maneuver may be from any point. When entering the maneuver at a point other than downwind, however, the radius of the turn should be carefully selected, taking into account the wind velocity and ground speed so that an excessive bank is not required later on to maintain the proper ground track. The flight instructor should place particular emphasis on the effect of an incorrect initial bank. Common errors in the performance of turns around a point are: failure to adequately clear the area, failure to establish appropriate bank on entry, failure to recognize wind drift, excessive bank and/or inadequate wind correction angle on the downwind side of the circle resulting in drift towards the reference point, inadequate bank angle and/or excessive wind correction angle on the upwind side of the circle resulting in drift away from the reference point, gaining or losing altitude, inadequate visual lookout for other aircraft, inability to direct attention outside the powered parachute while maintaining precise powered parachute control.